rings such as this are relatively easy parts to hold in the lathe. I've made this part by bandsawing the OD of the ring, clamping this in the chuck by the OD, and then machining this bore. With a bore that's this large, it's very easy to use the jaws of the chuck and clamp the part into the chuck by putting the jaws on the inside of the part like this. This part is now very firmly held in the chuck. Often, you'll want to make a similar part, but without a hole in the middle. Not having a hole means we can't attach it to the chuck by grabbing it with the jaws. We can't support this ring from the outside because that's the part we want to machine. Convenient way to hold a part like this is with the use of double-sided tape and a live center. Now we're not going to use the jaws of the chuck at all to actually grab the part. What we're going to do is press the part up firmly against the ends of the jaws. The double-sided tape there is to keep the part from spinning as we're cutting on the outer edge of the part. Now, if you look closely, I have a center punch mark here. That's the mark I used for the compass that I used to scribe the circle that I then cut out on the bandsaw. If I put the end of the live center in that center punch mark, apply some force to the part, pushing it up against the double-sided tape, and then lock the tailstock in place. With this setup, I can take quite a large cut and not worry about the part sliding on the jaws and damaging the part. And there's the finished disc. There are times when even a mark as small as this is a problem, is unacceptable. Cases like that, rather than pushing the live center up against the part, you can simply place another piece of stock in between the part and the live center. So the only purpose of the center in this application is to maintain contact between the disc and the double-sided tape. These are lathe arbors. Come in a standard range of sizes from about 1/8 of an inch up to 1 inch or more. What looks like a straight shaft actually has a very slight taper to it. This taper allows you to support parts with this sort of aspect ratio, typically parts that are a little wider than the bore in the part. This taper starts a few thousandths of an inch under the nominal size. In particular, the nominal size of this arbor is 5/8 of an inch. So one end of it is a little under 5/8 of an inch, the other end is a little over. Take any part that has a 5/8 nominal bore and press it on to the lathe arbor with an arbor press. This assembly can then very easily be installed in the Lathe Chuck. In this position, very easy to access this face of the part and the OD of the part. There are times when you'll want to be able to get access to the back side of the part as well. In particular, there are times when you want to make very sure that these two faces are parallel. You can do that by extending the arbor out of the chuck then supporting this into the arbor with a center. Now you have access to all three sides of the part. Now with parts such as this, where this dimension is at least as large as the bore, installing this on an arbor gives you very accurate support. However, if you have a part such as this, with a very low aspect ratio, meaning this distance here, the thickness, is smaller than the bore, if you attempt to support this on an arbor, it's very difficult to make sure that this part is perpendicular to the arbor. For this sort of part, it's better to make a custom arbor to support just this part. A custom arbor usually starts with a piece of bar stock like this. I've chosen this piece of stock so that this diameter is large enough to give me good support on this part. Now I begin by facing the part. And then using a tool with an angle here that's considerably less than 90 degrees, I can come in from the OD of the part like this. And machine a shoulder. Now I've just started roughing out this shoulder, so I'm still about 1/4 of an inch over the bore of the part that I'm eventually going to mount on this arbor. I'm now about 12 thousandths of an inch over the desired 1/2 inch bore. During this pass, which is a relatively light finishing pass, if you watch closely at the intersection of the face of the part and the shoulder, you'll see that I'm plunging the tool in below this surface. And then taking off the remaining 12 thousandths of an inch. This is a relatively sharp tool, but there's still a radius at the end of the tool. So I plunge the tool into the face to make sure that that radius doesn't contact this edge of the bore. This completes the precision part of the arbor. What remains is to drill and tap a hole here so that we can install the part and then with a bolt and washer clamp the part to the arbor. Here's the completed arbor with the threaded hole in the center. And using a bolt with a washer to distribute the load. Lock the part in place on the arbor. For very accurate work with lathe arbors, it's desirable to mount the arbor between centers. So rather than using a center at this end and a chuck or a collet in the headstock, we'll use centers at both ends. This center is identical to the center that's in the tailstock, but it's mounted in a special taper that fits into the headstock. Now the arbor can be mounted between these two centers. There's a problem here though. Just mounting it between the centers, we can't react to the torque produced by the cutting tool. So to deal with that, you use what's called a lathe dog. And there's a flat on the arbor that you line up with the set screw on the lathe dog. Tighten the dog in place. Insert the tail of the dog in the slot. Bring the center that's mounted in the tailstock into contact with the arbor. Lock the tailstock down and apply a little bit of force between the taper here and the arbor. Remember here that this is a dead center, unlike its counterpart, the live center, which has bearings in it, allows the center to turn freely. This is just a solid piece of steel. So if you apply too much force between the center and the arbor, you do damage to both of these parts. So you want a very small amount of force, and before you turn the machine on, you want to put a drop of oil in there to serve as a lubricant for that bearing surface. And with this setup, you can proceed to machine very accurately both sides and the OD of a part. Face plates are used often to secure parts in a lathe that are difficult or impossible to secure with either collets or chucks. For example, this is a piece of suspension out of a solar car. Very difficult to grab this any place convenient with a chuck. But using a face plate and hold down clamps attached through these T-slots, we can securely mount this on the faceplate. Here you can see the suspension part locked in place on the faceplate. As you can imagine by looking at this, this is a fairly dangerous setup. You should take great care in making sure that the part is held securely and that the cuts you take don't produce forces large enough to move the part around. You can see these hold-down clamps here are exactly the same type of clamp that's also used on the milling machine to hold parts down to the bed. Now in this setup, what I'm going to do is come inside here and machine a snap ring groove to retain a bearing. Many of the operations that were formerly done on a faceplate are now done in a milling machine using a boring head. For example, the bore here for the bearing 30, 40 years ago would have been done in a setup like this. Now, many of these operations are done simply by clamping a part like this stationary onto the bed of a milling machine, and then this type of feature is made with a boring head. A boring head cannot, however, make a feature like a snap ring groove or an O-ring groove, and that's why I'm using this setup here. Another use of the faceplate is to support very thin materials such as sheet metals or thin sheets of plastic. Using a layer of double-sided tape on the surface of the faceplate, you can attach these materials securely enough so that with a sharp tool you can come in and cut out thin rings of the material, typically for use in gaskets and shims. We start by covering the faceplate with double-sided tape. The spacing here isn't all that critical unless the material that you're supporting here is very, very thin. So with this sort of spacing, you'd be fine until you were trying to support a material that was 2 or 3/1000ths of an inch thick. This is a piece of aluminum sheet that's roughly 30/1000ths of an inch thick. See, it's quite flexible, and it would be difficult or impossible to support this something like a Lathe Chuck. But using the double-sided tape and the live center, can press this up against the faceplate and attach it securely to the faceplate with a double-sided tape. Now, if you watch closely here at the live center, I'm going to drive the live center quite a ways into this piece of sheet metal. Now, I'm not doing this to press it up harder against the double-sided tape. What I'm doing here is putting it in far enough so that in case the metal starts slipping relative to the tape, this disc, which is about the same size as something like a saw blade and running just about as fast, will not come flying out of the machine, but rather will be restrained by the live center. Before you start machining a part like this that is attached so closely to the surface of the faceplate, now make sure that you set the depth of the tool so that as you cut through this, you don't also cut into the faceplate. There, you can hear now the tool's come into contact with the double-sided tape. Now I've just set the depth stop so this tool can't go past that point and into the faceplate. I'm taking very light cuts here because although the inner part of this disc is secured over a large area by the double-sided tape, this ring out here that I'm very soon going to cut free from this disc will only be attached over a relatively small area. So by taking the light cuts, I run less of a risk of tearing this piece of the aluminum away from the double-sided tape. Okay. I've now hit the depth stop, so I've cut all the way through the disc and just into the double-sided tape. You can now move the tool in and start to make another cut. In doing so, produce a ring of metal that would be difficult to make in any other way. I have now completed both of these cuts. I'm back off the live center. And peel off this tape. And with a little bit of prying, should be able to free up the part. It's important to be patient here with the double-sided tape. You can hear, when I deflect the part, over quite a period of time, you can hear the tape pulling away. So if you try to pull the part free suddenly, you risk bending the part. You do this slowly, be able to free the part up with no distortion. Now, this is a useful technique whether you're making rings like this, use as spacers or gaskets or shims, something like that, or whether you want just the center part, a disc like this.